Imagine stepping into a machine that could transport you to the distant past or far into the future. A world where yesterday, today, and tomorrow are no longer boundaries, but mere points on a continuum you can traverse at will. Time travel, an idea that has fascinated humanity for centuries. But is it just science fiction, a product of our wildest imaginations? Or could it one day become reality? In 1905, Albert Einstein's theory of relativity changed our understanding of time and space. According to Einstein, time is not fixed. It stretches and contracts depending on speed and gravity. The faster you travel, the slower time moves for you. This phenomenon is known as time dilation. This means that if a spaceship were to travel close to the speed of light, time for its passengers would slow down compared to those on Earth. This concept has been proven in experiments with atomic clocks on fast-moving jets. Could this be the key to time travel? Another intriguing possibility is wormholes, hypothetical tunnels through space-time that could connect distant points in time and space. If we could stabilize one, we might be able to step through a portal to the past or future. However, the energy required and the risk of collapse make it purely theoretical, for now. But time travel isn't just about science. It's about logic and paradoxes. The famous grandfather paradox questions what would happen if you traveled back in time and prevented your grandfather from meeting your grandmother. Would you ever be born? This paradox suggests that changing the past could lead to logical inconsistencies, making time travel extremely complex. Scientists today are still exploring the mysteries of time. While we don't yet have a working time machine, concepts like quantum mechanics and closed time-like curves suggest that time travel might be theoretically possible in some form. Will we ever crack the code of time? Or will it forever remain a dream of the imagination? Only time will tell. Time dilation is a difference in the elapsed time measured by two observers, due to a relative velocity between them or to a difference in gravitational potential between their locations. This phenomenon has been confirmed by various experiments, such as observing the decay rates of particles moving at high speeds. The faster an object moves, the more time slows down for it relative to a stationary observer. This effect becomes more pronounced as the object approaches the speed of light. In fact, astronauts on the International Space Station experience a very slight time dilation due to their high orbital speed. While this effect is minuscule, it demonstrates that time dilation is a real and measurable phenomenon. To illustrate, imagine two synchronized clocks. One stays on Earth, while the other travels on a high-speed jet around the world. When the jet lands and the clocks are compared, the one on the jet will show a slightly earlier time. This is time dilation in action. But time dilation isn't just limited to speed. Gravity also plays a role. According to general relativity, the stronger the gravitational field, the slower time moves. This has been observed in experiments where clocks at different altitudes show slightly different times, with clocks closer to the Earth's surface ticking slower due to the stronger gravitational pull. If we could harness the effects of time dilation, future space travelers might experience time very differently from those on Earth. Imagine traveling to a distant star at near light speed and returning to find that decades have passed on Earth, while only a few years have elapsed for you. It challenges our perception of time as a constant and invites us to think of it as a flexible dimension, influenced by speed and gravity. Time dilation is just one piece of the puzzle, and the quest to understand the full picture of time travel continues. Now, let's delve into the concept of wormholes. Also known as Einstein-Rosen bridges, are theoretical passages through space-time that could create shortcuts for long journeys across the universe. They are solutions to the Einstein field equations, which describe how matter and energy interact with the fabric of space-time. Imagine space-time as a two-dimensional sheet. If you fold this sheet and create a tunnel between 2 points, you have a wormhole. This tunnel could theoretically connect vastly distant regions of space, making travel across the universe almost instantaneous. However, the reality of wormholes is far from simple. The energy required to create and maintain a wormhole is beyond our current technological capabilities. To keep a wormhole open, we would need a form of negative energy, which has only been observed in minute quantities in quantum experiments. This negative energy would counteract the natural tendency of the wormhole to collapse. Moreover, the risks associated with wormholes are substantial. The structure could be highly unstable, and any slight disturbance might cause it to collapse, potentially trapping anything inside. Additionally, traveling through a wormhole could lead to time paradoxes, where cause and effect become entangled in ways that defy our current understanding of physics. Another fascinating aspect of time travel is the concept of closed time-like curves, or CTCs. Imagine a path through space-time that loops back on itself, allowing an object to return to its own past. It's a solution to the equations of general relativity. In theory, CTCs could make time travel to the past possible. Picture space-time as a flexible fabric. If it bends and twists in just the right way, you could end up at an earlier point in time. However, while CTCs are mathematically possible, their physical existence remains a mystery. One of the significant challenges with CTCs is the potential for paradoxes and inconsistencies. For instance, the infamous grandfather paradox questions what would happen if you traveled back in time and prevented your grandfather from meeting your grandmother. Would you cease to exist? Such paradoxes make the concept of CTCs highly controversial. Some physicists argue that quantum mechanics might offer solutions to these paradoxes. Quantum mechanics, with its principles of superposition and uncertainty, could provide a framework where multiple timelines or outcomes coexist, potentially resolving the inconsistencies posed by CTCs. The study of closed time-like curves continues to be an area of active research in theoretical physics. Finally, let's consider the implications of time travel on our understanding of the universe. If time travel were possible, it could have profound effects on causality, free will, and the nature of reality itself. The ability to travel through time could allow us to witness historical events. However, it could also pose significant ethical and philosophical challenges. Imagine the power to alter the course of events that have shaped our present. The potential for misuse or unintended consequences is vast. And if we did, what would be the ripple effects on our timeline? The ethical dilemmas are as complex as they are intriguing. If we can travel back and forth in time, does it mean that our choices are predetermined? Or do we create new branches of reality with every action we take? The nature of reality itself could be fundamentally altered by the existence of time travel, challenging our understanding of existence. Would meeting a past or future version of ourselves change who we are in the present? As we continue to explore the mysteries of time, we may one day unlock the secrets of time travel and transform our understanding of the universe. Thank you for watching.